You ever look up at a satellite streaking across the sky or watch a drone do these complex maneuvers and think, how do we know exactly where it's going? Well, it all boils down to the calculus of motion. And in this explainer, we're going to build a complete toolkit from scratch to describe and analyze the journey of, well, pretty much anything moving through space. So let's jump right in. So, yeah, how do we actually do that? How can we take something super dynamic, like a roller coaster's wild ride, or even something as kind of chaotic as a fly buzzing around, and pin it down with perfect mathematical precision? That's the big question here. And the answer, it turns out, is hiding in these amazing things called vector functions. They're what let us unleash the power of calculus on motion. Okay, so our journey has to start somewhere, right? And for us, it starts with the most basic, fundamental building block of all, getting from a general path to a very specific position. I mean, before we can talk about speed or anything fancy, we first have to nail down exactly where our object is at any given second. Everything else is built on top of this. And we do that with something called the position vector, which we write as r of t. You can just think of this as a perfect GPS system. You plug in a time, t, and it spits out the exact x, y, and z coordinates of your object. It's incredible, really. This one little function contains the entire blueprint for an object's whole journey. All right, now for the part that's, well, really cool. If that position vector tells us where something is, calculus is what tells us how it's moving. And honestly, if you're already comfortable with basic derivatives from single variable calc, this next part's gonna feel super familiar. We're literally just applying the same rules, but we're doing it 3 times, once for each component of our vector. And look at how elegant this is. The relationship is just, it's beautiful. The velocity vector, v of t, which tells you both speed times direction, is just the first derivative of position. Simple. And the acceleration vector, a of t, which tells us how that velocity is changing, well, that's just the derivative of velocity. Or you could say the second derivative of the original position. It's such a clean and powerful way to connect all these ideas. Theory is great and all, but let's get our hands dirty and make this real. We're going to take a position vector and work our way all the way down to its velocity and acceleration. So here we go. We start with our position vector, r of t. To find the velocity, we just go piece by piece and take the derivative. The derivative of t squared is 2t. The derivative of e to the t is just e to the t. But look at that last component, t times e to the t. This is where so many people trip up. It's a classic trap. You have to remember to use the product rule there. Once you do that, you get your final velocity vector, v of t. Now for acceleration, we just do the exact same thing again, only this time we're taking the derivative of our new velocity vector. The first 2 parts are easy enough. And that last component? Yep, you've got to use the product rule again. After you work it out and simplify, you land on your final acceleration vector, a of t. See? It's just a process. All right, so we've mastered going forward, from position down to acceleration. But what if you have the opposite problem? What if you know the acceleration? Maybe from knowing the forces on an object. But what you really want is to figure out the path it took. You probably guessed it. To go backwards, we just reverse the process with integration. But, and this is a huge but, there's a catch. Every time you integrate, you get that pesky plus c, that unknown constant. To figure out the one specific path our object took, we need some extra clues. We need some starting information, what we call initial conditions, like where it started and what its velocity was at the beginning. Let's see how that works. We're given an acceleration vector, and we integrate each component. That gives us a general idea of the velocity, but with 3 unknown constants floating around. This is where our initial data comes in to save the day. We're told the velocity at time 0, so we plug in t equals 0, set our equation equal to that known vector, and boom, we can solve for each constant. That locks in our exact velocity function. And from there, it's rinse and repeat. We integrate our velocity vector one more time, which gives us a new set of constants. But we have another piece of information, the object's starting position. We use that to solve for these new constants. And just look at what we did. We started with just an acceleration and 2 little data points, and from that we've managed to completely reconstruct the object's entire path through space. That is seriously cool. Okay, so far we've just been calculating acceleration as a number, a vector. But now let's go a level deeper and ask, what is it really doing? Because it turns out that acceleration isn't just one simple thing. It actually has 2 totally different jobs that it's trying to do at the exact same time. And this right here is the key insight for this whole section. Any acceleration you feel, any acceleration an object experiences, can be broken down into two parts that are perpendicular to each other. One of those parts is all about changing your speed, speeding up or slowing down. The other part is all about changing your direction, making you turn.
We give these two parts names, the tangential component and the normal component. The tangential one, AT, acts along your path. It's the gas pedal and the brake. It's what pushes you forward or slows you down. The normal component, AN, acts perpendicular to your path, always pulling you inward, into the curve. It's the steering wheel. So think, gas and brake is tangential, steering is normal. As a perfect analogy.
So how do we pull these two numbers out of the vectors we've been working with? Well, lucky for us, we have some really powerful formulas that use tools we should already know, the dot product and the cross product. The tangential component uses the dot product of r prime and r double prime, while the normal component uses the magnitude of their cross product.
Let's just run through one real quick. We take a position vector, we find its first and second derivatives at a specific time, t equals 1. Then we calculate the dot product, calculate the cross product, and finally, we plug those results into our formulas to get the exact values for AT and AN. What this tells us is incredibly powerful. At that precise moment, we know exactly how much of the total force on the object is going towards changing its speed versus how much is making it turn. Whoa! We have covered a ton of ground. So let's take a step back, zoom out, and put everything we've just learned together into one cohesive, powerful toolkit for looking at motion. And here it is. This is your toolkit. Everything starts with position, rift of t. You differentiate to go forward to velocity and then to acceleration. You integrate to go backwards. But you always have to remember you need those initial conditions to pin down the constants. And finally, never forget that acceleration has two distinct jobs. It changes speed and it changes direction. And look, why does any of this really matter? Because this is not just some abstract math problem. This is literally the language of the real world. This toolkit is exactly what engineers and physicists use every single day to design safer cars, to plot the path of a spacecraft to Mars, and to model the most fundamental forces in our universe. So I'll leave you with this to think about. Now that you have these tools, what else could you describe? Think about the beautiful arc of a baseball, or the intricate motion of a school of fish, or even the path of a hurricane. Once you can describe motion with math, you can start to understand and predict the world around you in a totally new and powerful way.